Hey, Pat, welcome back. So in this video, I will be doing AMC 10B 2021 fall, numbers 15 and 16. Okay, so here's where it starts getting a little trickier, but honestly, I don't even think these ones are that bad. I think a lot of these problems, you know, they can really be reasoned through. And this is another problem where similar triangles comes really in handy. So like the more you know about similar triangles, the more it can really help you with a lot of these geometry type problems. So number 15 says, in square ABCD, points P and Q lie on AD and AB respectively, segments BP and CQ intersect at right angles at R, with BR equals 6 and PR equals 7. What is the area of the square? Okay. Um, all right, so here's what I did. I started by connecting, let me do this. So I started by connecting PC and PQ, right? Just to see if that might help me at all, right? Now, one thing that I noticed is that, well, actually, you know what? Instead of doing that, what I think I'm going to do is, now this might seem a little bit strange, but I'm actually going to draw the line from Q going straight up to CD, right? Sometimes with these problems, you have to think outside the box a little bit. And I'm going to label this point, I guess S, right? So I'm going to label that point S. Now, I'm going to name this angle down here alpha, right? Note that this is 90 degrees, right? And this is also 90 degrees. And this is also 90 degrees, right? And this is 90 degrees. A lot of little 90-degree angles, right? Which is always really helpful. Now, one thing I know is that if I look at this right triangle here, right? If I look at this right triangle here, if I kind of draw that triangle separately, right? And I have this sort of piece here, and I call this angle alpha. One thing that you can sort of prove to yourself is that this angle would also equal alpha. Right? And the reason for that is because, remember, this angle is 90 degrees, right? So let's say I call this angle in here beta, right? Well, what do I know about alpha plus beta? I know that they have to add to 90 degrees, right? But notice how this is also 90 degrees, right? So therefore, this angle and this angle have to add to 90, right? Which means that this angle here must be alpha. So I know this angle in here is alpha, right? Okay, which means, what does that mean? That means that this angle here would be beta, right? Right, this angle here would be beta, this angle here would be beta. So now what does that tell me? Well, if I look at this big triangle here, right? This triangle, ABP, right? And then I look at this triangle here, QCSQ or QSC, right? I actually know that those triangles are not only similar, but they're actually congruent. And the reason I know that is because, well, first of all, they are similar triangles, right? Which we can clearly tell by, right? We know that this angle is alpha, we know this angle is alpha, we know this angle is beta, we know this angle is beta, and then 90, 90. So therefore, all the angles are equal. So the triangles are clearly similar. And then I know that this distance AB, let's say I call it A, right, is equal to this distance here, right? Because the whole thing is a square. So that distance would also be A. And what that tells me is that this distance, if let's say I call this distance here, let's say I call it B, right? Then this distance here is also B, right? right? So then what does that tell me? Well, that tells me that I can then call this, so QB, right? This sort of piece here, right? I can call this distance here B, right? And then this distance here would be A minus B, okay? Now, what I'm going to do is I'm going to look at, I'm going to erase some of this stuff here. I'm going to look just at this triangle here, triangle PAB, right? I'm going to look at that triangle, knowing sort of what I know now. So I'm going to kind of make this, right? And then I have here, so this is what? A, P, B, Q, R, right? And then I know this is 7. I know this is 6. I know I'm calling this B, and then this is B, right? And, the whole thing would be A, right? And then I'm going to call QR, I'm just going to call it C just to give it a name, right? So now I have, at least a representation for each different side, right? Now, can I set up any, and I do again know that this triangle here, right? This triangle QRB, right? Triangle QRB is similar to triangle. So remember, this angle is equal to, well, that equals itself, and then this angle is equal to this angle, right? So QRB would be similar to PAB, right? PAB. And that will allow me to set up some proportions, right? So, well, let's think about this. Can I start by using Pythagorean theorem on the big triangle PAB, right? Like, do I know that A squared plus B squared is equal to 13 squared? Right? Right, because it's A, B, 13, right? So I can use Pythagorean theorem. So in other words, A squared plus B squared is equal to 169, right? Can I set up another ratio involving A and B? Well, yeah, because what I can do is by looking at the big triangle, right, the larger triangle, I can say A over B is equal to what? A over B is equal to, actually, that's not what I want. What I want to do is I want A over 13, right? So A over 13 would be equal to 6 over B, right? A over 13 would be equal to 6 over B. Okay, right? And can we see where that comes from? Right? A over 13 is equal to 6 over B, right? Because it's because of the similar triangles, right? So what does that tell me? That tells me AB is equal to 78, which I can rewrite as B equals 78 over A, right? And now what I'm going to do is I'm going to substitute this for B here, right? So I'm going to do A squared plus 78 over A squared equals 169, right? Or A squared plus 78 squared over A squared equals 169. Now I'm going to multiply everything by A squared. So I'm going to get A to the 4 plus 78 squared equals 169 A squared. So I'm going to erase, I'm going to erase over here because I need more room. So, okay, so I'm going to erase this. So now so essentially what I have is I have a to the 4 minus 169a squared plus 78 squared equals 0. And I'm going to do a substitution. I'm going to let m equal a squared, which is actually the answer to the problem. So if I can calculate m, I get the answer to the question. So m squared minus 169m plus 78 squared equals 0. Now, you might look at this and say, how the heck am I supposed to solve this? Well, think about it. We know 169 is 13 times 13, right? Let's think about 78. 78 is 39 times 2, or 13 times 3 times 2, 13 times 6, right? So essentially 78 squared is equal to what? 13 times 3 times 2 times 13 times 3 times 2. So let's think, can we somehow turn that into 13 times 13? Right? Is there a way we can add a combination of these to get 13 times 13? Well, can we do 13 times 3 times 3, right? Plus 13 times 2 times 2, or in other words, 13 times 9 plus 13 times 4, or 13 times 13, right? So we can split 78 squared into 13 times 9 times 13 times 4, right? So sometimes you just have to do a little, arithmetic on the side because you can't use a calculator. Okay. So we can split this up to be m minus 13 times 4 times m minus 13 times 9 equals 0, right? So that is going to mean m is either going to equal what? 52, right? 52, or m is equal to 117, right? But by looking at the answer choices, the only one that's there is 117. So therefore the answer must be D, 117, right? So that one's like, would I say it's crazy hard? No. Using similar triangles is definitely a good way to go about it though. Right? And you have to do a little bit of like arithmetic because again, you don't have the calculator, so, right? Okay, 16. 5 balls are arranged in a circle. Chris chooses 2 adjacent balls at random and interchanges them. Then Silva does the same with her choice of adjacent balls to interchange being independent of Chris's. What is the expected number of balls that occupy their original positions after these 2 successive transpositions? Ooh. All right, so expected value means we need to calculate, we need to multiply each possible value by its probability of occurring and then add them together. So let's think about it. What are the possible numbers of balls that could be left in their original positions, right? Let's just go one by one and determine like what could be possible. Well, let's see, can 0 of them be left in the same position? So can all of them be rearranged? Well, if you think about it, no, because at most they can only move 4 balls. So one of them has to stay in its position. So 0 is not possible, right? So we'll do 0 times 0, right? Is it possible to leave exactly 1 ball in the same position? Yes, because think about it. Let's label the balls A, B, C, D, E, right? Let's say Chris switches A and E and Silva switches B and C. If that's the case, then only D will be left in its original position. So now we just need the probability of that happening, right? What's the probability that Silva would switch a totally separate pair that doesn't intersect with the pair that Chris switched? So for any pair that Chris switches, right, Silva needs to switch a pair that does not intersect with this pair, right? Well, if we think about it, that leaves us with 2 possible, like, how do I say this? So if I imagine like the pair that's being, let's say that I associate the pair being swapped with the ball that's on the left of that pair. So basically I would say that Chris is picking ball E, which means he's going to switch E and A. Right? So then that means that I don't want Silva to pick A because, right? Because if Silva picks A, then that intersects with the pair that Chris already switched. We don't want that, right? We want Chris to either pick B or C, right? Because if he picks B, he'll switch B and C. And if he picks C, he'll switch D and C. If he picks D, he's going to switch D and E, which intersects with Chris's pair. So we want him to either pick B or C, which is 2 out of the 5 possible balls. And notice how that's true no matter which pair Chris picks. If Chris picked A and B, we want Silva to pick either C or D. If Chris picked B, then we want Silva to pick either D or E. So it's always 2 out of the 5 choices. So we'll be left with one ball 2/5 of the time, right? What about 2? Is it possible that exactly 2 are left in their right position? Yes, that is possible. Because imagine that Chris switches A and E, right? So let's say Chris picks E, meaning he'll switch A and E, right? Now imagine that Silva picks A, meaning he switches A and B, right? Which is actually now, so E was now switched with A. So this is now A, E, and then Chris switches E and B, which means this is now B, E. So notice how A, B, and E are all in different positions now, which means only C and D are left where they were supposed to be in their original positions. So what we would need is we would need Silva to pick a ball that intersects with the pair that Chris picked, right? So we need him to either pick, so if Chris switches A and E, we need Silva to pick either A or D, because if he picks A, he'll switch A, B. If he picks D, he'll switch D, E, and then those 3 balls will get switched around, and then the other 2 will be left. So if you think about it, again, that's a 2 out of 5 probability, because it's one of the 2 that intersect with the one. You don't want him to pick the same one Chris picked. You want him to either pick the one to the left or to the right of it. So that's 2 out of the 5 possible balls to pick, right? Is it possible to leave exactly 3 in the same position? No, that's not possible, because for that to be the case, exactly 2 of them would have to be switched. And if you think about it, that's not possible. There's no way to switch exactly 2 of them. Right? And you can sort of convince yourself of that, because like if they switch the same pair back and forth, then they're all back where they started. And if you switch any 2 pairs that intersect, then all 3 of those balls end up in the wrong positions. So there's no way for 3 to happen. So we're going to put 3 times 0. Same thing for 4, because there's no way for just one ball. Like if you think about it, it's not physically possible that only one ball is in the wrong place. If one ball is in the wrong place, something else also has to be in the wrong place. So 4 is definitely not possible. Now, what about 5? Is it possible that all the balls end up in their same position? Yes. And how is that possible? Well, that's possible if they pick the exact same pair. So if Chris switches A and B and Silva switches B and A, then they're just back, right? So if we think about that, that means he has to pick the exact same position that Chris picked, right? Or Silva has to pick the exact same position that Chris originally picked, right? Because if Chris picked A and B will switch, then Silva needs to pick B, and then B and A will switch back again. So that's a 1 out of 5 chance that she picks exactly the same position that Chris picked, right? So this is our answer, right? This is our expected value. So we're just adding these up. So we get 0 plus 2 out of 5 plus 4 out of 5 plus 0 plus 0 plus 1 out of 5. And if we add these up, we get 7 out of, no, what? Oh, sorry, that's 5 out of 5, not 1 out of 5. So if we add those up, that gives us 11 out of 5, right? And 11 out of 5 is equal to 2.2, D, right? So the answer to number 16 is D. Again, like, I don't know. I don't think, I think it depends on maybe, what types of math you find more difficult. Like I tend to be pretty good with probability type problems. So I didn't find these ones super hard. I think the next few coming up are going to get a little more involved. So, right. But these ones I think were not too hard. All right. Okay, so that'll be it for this one. My next video will be numbers 17 and 18. And I will see you later.